So how observable is your software? I mean, it sounds like a simple enough question, right? But if you're a software engineer, an architect, or frankly anyone who's ever had the absolute pleasure of debugging a complex modern system at 3 a.m., you know that this question is anything but simple. Picture this. You're staring at a dashboard. It's entirely green. Everything looks perfectly fine. But simultaneously, your customer support team is just screaming that the app is completely down for a huge segment of users. We've all been there, and it is incredibly painful. Well, today's explainer is dedicated to that exact pain, and more importantly, how we can completely eliminate it. We're going to dive deep into what is essentially the definitive guide on this topic, specifically unpacking Chapter 1 of the groundbreaking second edition of Observability Engineering. Okay, let's get into it.
This quote right here perfectly captures the absolute nightmare of modern software development. It says, in low observability systems, this often manifests as alert storms. When a critical dependency fails, do you know exactly where to look? Or do you have to check multiple sources and sleuth your way to the source of the cascade? Just think about the last time a critical dependency failed in your stack. Understanding why an issue is happening, that's usually the hardest part of the job. And once you actually find the source of the fire, you then have to figure out what caused it in the first place. Identifying that causal trail is tough enough, but our source text points out this fascinating meta process where teams struggle even more, which is figuring out how they figured it out. Like, how do you encode that specific trail of breadcrumbs into the system itself instead of just letting it live exclusively in the heads of your senior engineers? Because if debugging relies entirely on the gut intuition of your most tenured staff, well, your system isn't observable. It's really just a mystery waiting to happen.
So clearly, we need a complete paradigm shift. We have to fundamentally reframe observability entirely, especially right now as we rapidly enter the AI era. We've got to stop thinking about observability as just, another category of monitoring tools or some fancy new dashboard you buy. It is so much bigger than that. The source material makes this incredibly powerful case that observability is actually a foundational practice of software development. It's the intelligence layer of your entire production environment. And as AI massively accelerates how software gets built, production becomes literally the only place where your intent actually means reality. Here is our roadmap for today. We're going to cover 1. Origins of observability. 2. A property of dependability. 3. The 3 pillars model. 4. The unified storage model. And finally, 5. AI and developer intent. Starting off with Section 1. The origins of observability and where this whole concept actually began.
It is kind of wild to think about, but the term observability isn't some fresh Silicon Valley buzzword. It was actually coined way back in 1960 by an engineer named Rudolf E. Kálmán. This was in a paper that's now widely considered the birth of modern control theory. And if you're not familiar, control theory is basically the mathematics of systems that you're trying to steer towards a desired state, despite all the noise, disturbance, and incomplete information flying around. Sounds a lot like managing cloud infrastructure, right? Kálmán's key insight was that observability and controllability are mathematical duals. Put simply, a system you cannot observe is a system you literally cannot control. For Kálmán, observability meant asking one very specific question. Given the outputs that you can measure, can you infer the complete internal state of the system? If yes, great, the system is observable. If no, that means some internal state is permanently hidden from you. And the scary part is, no amount of clever engineering will recover it later because you never captured the information to begin with. The source text makes a great point here, emphasizing that while software obviously isn't bound by the physical constraints of atoms or electrons, it has its own massive constraints when it comes to complexity. So Kálmán's 1960 definition turns out to be the absolute perfect lens for reasoning about modern software.
Moving on to Section 2, a property of dependability, introducing the 7th property. In systems engineering, there's this widely accepted framework for software dependability. It's often associated with Lapri's list. It includes all the familiar heavy hitters: reliability, availability, security, maintainability, performance, and interoperability. These are the core attributes that actually make software trustworthy. But the authors of our source material argue, and honestly, it's a very compelling argument, that it is time to officially add a 7th property to that list: observability. In the software context, they define it as the ability to understand or debug any given system state. And look, this isn't just some minor academic tweak to a textbook list. It is totally foundational. Just think about it for a second. How can a system truly be considered maintainable, or reliable for that matter, if you can't even understand its internal state when something breaks? Now, you can't measure observability strictly with a single number, much like you can assign a simple score to security. But you can measure it qualitatively. Ask yourself, can you answer brand new questions about your system without having to ship new code to do it? Can you isolate exactly where a failure is happening without relying on a senior engineer's gut feeling? Because if not, your software has a low degree of observability, and that fundamentally compromises its overall dependability.
All right, Section 3, the 3 pillars model, which is the legacy approach we've all been dealing with. So, the tech industry has traditionally relied on what are commonly called the three pillars of observability, which are metrics, logs, and traces. But take a look at the fatal flaw here. They are isolated silos. The source text actually refers to this as the first tectonic plate of telemetry. Every single signal is shipped off and stored in its own completely separate silo. Your metrics go to a time series database, your logs get dumped into a log aggregator, your traces go off to some tracing service, and if you have an error, well, that probably goes somewhere else entirely. But here is the critical context we have to remember. These tools were originally built for infrastructure operators, not software developers. Back in the day, operations teams ran the whole show: routers, hardware, bare metal operating systems. For them, metrics and simple logs made perfect sense for monitoring a router. But today, developers need to understand wildly complex business logic, like a microservice billing system or a highly customized user checkout flow. When your data is fractured across 3 different silos, you completely lose the relationships between those data points. You're forced to manually correlate a spike you see in a metric dashboard with some scattered, random line in a log file. It's an approach built entirely on the assumption that you already know what you're looking for. But as we all know, in complex modern systems, failures are almost always things you've never ever seen before.
Which brings us to Section 4, the unified storage model, getting back to first principles.
Instead of those frustrating isolated silos, the solution is a unified storage model, which is typically powered by a columnar database. In this model, all the telemetry that describes a single request is stored exactly once. It preserves as much context and as many relationships as possible. These are stored as arbitrarily wide, structured log events, sometimes they're called canonical logs, or as spans and traces. Just think about the massive leverage this gives you. The source material notes that the true cost of software isn't writing it, it's the cost of maintaining it over time. Telemetry is literally your code talking back to you from production, telling you exactly what's happening in the real world. Therefore, how you choose to store and analyze that data is absolutely not an infrastructure decision. It is a vital, core product decision.
Let's actually put these two tectonic plates head to head for a second. The legacy 3 pillars model relies heavily on aggregated data. It's siloed, and crucially, it is predictive, meaning it really only works well when you can predict what's going to break and write a specific dashboard for it ahead of time. It's essentially a system for known unknowns. On the flip side, the modern unified model relies on high cardinality data. It is deeply contextual and built entirely for exploratory analysis. It handles the unknown unknowns. And the authors make a fascinating point here. In the unified model, if you have a wide, structured event with, let's say, 29 attributes, and you add a 30th attribute, that single new attribute adds as much value as the entire preceding 29 attributes combined. It is a mind-blowing amount of mathematical leverage. Why? Because every new attribute exponentially increases your ability to slice, dice, and group the data to find the exact needle in the haystack. These two models, they aren't just different tools. They are not compatible. They represent fundamentally different assumptions about what telemetry is even for in the first place.
Let's look at how this builds into something incredibly practical for your day-to-day. Here's an example of one wide, traceable, structured log event. It's represented here as a JSON payload for just a single API checkout request. Look at the immense amount of context packed into this one single event. You don't just know that a 200 OK status happened. You know the exact user ID, their specific subscription plan, and their country. You have application context. Was that shiny new checkout feature flag enabled? How many items were in their cart? You even have the exact deployment build ID that served this specific request. So the crucial takeaway is this. With rich context and high cardinality data, you have the superpower to pick out any arbitrary subset of requests with extremely high precision. If suddenly checkouts start failing, you don't just stare at a spiking error graph and panic. You query the data and instantly discover, for example, that 100% of the failures are coming from users in Finland who are on the Pro plan, using mobile devices, hitting a specific build ID where a cache missed. Boom. You didn't need to predict that highly specific combination of failures to find it. The data was already unified and just waiting for you to ask the question.
And finally, Section 5, AI and developer intent. Why this is an urgent need right now.
I really want you to let this sentence sink in. Observability is the validation of developer intent. For the past decade, people usually argued for observability by saying, oh, it improves incident response, or it helps developer productivity. And while that's absolutely true, it vastly understates what is actually at stake today. Because as we integrate large language models and AI agents into our daily workflows, the very definition of what it means to write software is changing.
When AI agents are writing, testing, reviewing, and shipping code faster than humanly possible, the intent of the human developer becomes completely decoupled from the actual execution of the code.
AI radically upends the entire software development lifecycle, or the SDLC. Because these agents can write and ship code so incredibly fast, verifying that code suddenly becomes the massive new bottleneck. You see, agentic behavior is inherently unpredictable. It evolves. It changes over time based on prompts and context. You literally cannot just read an agent's code and intuit how it's going to behave at scale in a complex distributed system. Therefore, observability becomes your absolute last line of defense. It is the ultimate feedback loop. The source text explicitly states that agents running in production can only ever be as good as the data they have access to. They need context, they need relationships, and they need a diversity of sources. All that wisdom and connective tissue that your senior engineers carry around in their heads, like knowing to check latency by build ID after a risky deploy, that tribal knowledge must be encoded into the system's telemetry. If you don't have a high degree of observability, releasing AI agents into your production environment is essentially flying blind at supersonic speeds.
We are nearing the end of our explainer, and I want to highlight this phenomenal quote that basically summarizes the core philosophy of everything we've discussed today. Production is reality. Observability is how you understand it. Everything else follows. Look, you can run all the tests you want in staging. You can have the most rigorous multi-stage code review processes in the world. But once code, and especially AI-generated code, hits production, that is reality. Staging is just a sandbox. Production is where the rubber meets the road. Observability isn't just some troubleshooting tool you break out during an incident. It is the fundamental sense-making capability of your entire socio-technical system. It is how you create that vital feedback loop that connects what you meant to build with what your users are actually experiencing.
I want to leave you with a really provocative thought based directly on the source material. The authors warn that aggregates conceal a multitude of sins. Think about that. If all your legacy tools tell you is that your system is 99.9% successful overall, you might be completely missing the fact that a specific critical workflow for a specific subset of high-value users is failing 100% of the time. So, I challenge you to look at your own systems today and ask yourself honestly, if you are still relying on isolated metrics, disconnected logs, and aggregated dashboards, what is your telemetry hiding from you? What unknown unknowns are lurking in your production reality right now? Thank you so much for joining me for this explainer, and I highly encourage you to look deeper into the unified data models we've discussed today to finally give your systems the observability they actually deserve.